Hello everyone, welcome back to the Iron Conflict and Frontline channel. Make sure you hit subscribe and like my videos. Today we're diving into one of the most alarming weapons to emerge from the current arms era, Russia's so-called flying Chernobyl missile, officially known as the 9M730 Burevestnik NATO designation, SSC-X-9 Skyfall. Strap in, this is a review/explanation that covers everything: exterior, interior, performance, safety features or lack thereof, unique selling points if you can call them that, price or cost estimate, and finally, our conclusion about whether this is truly the game changer Russia claims, or a complete disaster. From the moment the first reports surfaced, the story hook here writes itself: a missile powered by a nuclear reactor, purportedly able to fly for essentially unlimited range, evade missile defenses, and loiter. But with that promise comes enormous risk to those around it, to the environment, and arguably even to Russia itself. The nickname Flying Chernobyl is not just clickbait, it hints at the nuclear radiation risk built into the design. Today we'll peel back the layers and see what this weapon really is. Let's start with the exterior. Outwardly, the Burevestnik appears as a large cruise missile body, roughly 12 meters in length for the version listed in open sources. It is designed not as a ballistic missile with a steep trajectory, but as a low-flying cruise missile, powered by a compact nuclear reactor and a ramjet propulsion system. The exterior fuselage has to accommodate both warhead, reactor module, heat shielding and cooling systems, plus wings or control surfaces to allow aerodynamic flight at low altitude for extended periods. Visually, one sees what looks like a long, slender missile body mounted on a heavy transporter or launch rail in Russian official footage. In satellite imagery, analysts identified a probable fixed launch site with horizontal launch pads, bermed protection walls and roads linking to warhead storage bunkers north of Moscow, near the facility known as Vologda 20/Chibzara. The launch platform and infrastructure are part of the exterior story too: heavy lorries or mobile launchers, but likely also fixed concrete launch pads, indicating the weapon may be deployed from hardened silos or pads rather than fully mobile trucks, which raises questions about how stealthy or mobile the system really is. Observers note that the imagery shows dedicated facilities roads, servicing buildings, which suggests large, fixed logistic commitments. A key external design feature or flaw, depending on view, is the fact that the reactor exhaust or coolant could create a radioactive plume, making detection more likely rather than less. Indeed, analysts note that the concept of a nuclear-powered ramjet may generate detectable radiation, which undermines the idea of being undetectable. From a purely external viewpoint then, impressive on paper, ominous in reality. The long fuselage, the promise of low-altitude flight, the dedicated infrastructure all point to a major strategic effort. But there are already signs of risk. Infrastructure is fixed and visible. The nuclear propulsion, apart, introduces major problems. We will get to those. Now, moving into the interior. This is the longest section of our review, because it is where all the complexity, promise, and peril converge. Inside the Burevestnik, engineers had to pack a nuclear reactor module, a propulsion system likely a ramjet or turbojet augmented by reactor heat, fuel systems or reactor coolant, control electronics, guidance and navigation systems, the warhead compartment, structural support, aerodynamic surfaces, and heat shielding. According to open-source data, the missile is designed to carry a thermonuclear warhead. The term interior here really covers the entire architecture: what sits beneath the skin, what makes it tick, and what risks lie hidden inside. First, the reactor. The choice to use a compact nuclear reactor gives the missile theoretically unlimited range because it doesn't depend on conventional fuel in the same way typical cruise missiles do. The Russian Defense Ministry has claimed the range is effectively unlimited, but that same reactor means there must be robust shielding and heat management systems so that the missile does not self-destroy or leak radiation. The interior must include coolant loops, radiation shielding for sensitive components, and containment for any radioactive byproducts. If one imagines it, The module inside is akin to a small nuclear power plant with missiles, guidance, and warhead attached. Second, the propulsion. The reactor's heat would be channeled to a ramjet or similar high-speed air-breathing engine, possibly with afterburner capability, to sustain flight at low altitudes for long durations. That flight profile is designed to evade radar by flying close to terrain, changing course, and using the reactor to provide long endurance. Sources say it uses a compact nuclear reactor and a ramjet to do just that. Inside the missile, you'll find intake ducts, compressor and turbine stages, or their equivalents adapted for nuclear heat source, guidance computer, flight surfaces, sensors for terrain following and radio altimeter, communications links for mid-course corrections and possibly loitering behavior. Third, the warhead compartment. The interior must include a thermonuclear warhead or at least the interface to one. This means high-yield explosive package, triggering mechanism, safety interlocks, electronics to arm and disarm, and a connection to the guidance/navigation system. In a missile with loiter or long endurance flight, the interior also needs to include power supplies, autonomous controls, and a backup system in case primary systems fail. Additionally, since the missile is nuclear-powered, there must be sensors and fail-safe systems to detect radiation leaks, overheating, structural damage, or guidance malfunction. Fourth, structural and thermal management. At low altitude and high endurance, the interior structure must support large thermal loads, vibration, aerodynamic stress, possible maneuvers, and maintain integrity of the reactor and warhead. Heat shielding becomes critical. The reactor and exhaust must not melt internal components, nor emit telltale infrared signatures that make detection trivial. Inside the airframe, you would find layers of insulation, coolant pipes, perhaps active cooling systems, and redundant structural supports. Materials used would need to be heat-resistant, radiation-resistant, high-strength alloy or composite. Fifth, navigation and guidance systems. The missile must navigate vast distances, possibly avoid detection, follow terrain, change direction unpredictably, and penetrate air defenses. Inside the missile is likely an inertial navigation system, INS, possibly stellar or terrain, map updates, plus mid-course or terminal guidance sensors. If it loiters, it may include a flight computer that manages fuel/energy, in this case, reactor output, and makes decisions or receives updates via data link. Reliability is critical. If guidance fails mid-mission, the missile could veer off, crash, or behave unpredictably, raising safety concerns. Analysts note the missile has had difficulty achieving successful tests. Sixth, safety and fail-safe devices inside. Ideally, there would be multiple safety interlocks so the warhead cannot detonate accidentally, the reactor does not melt down, the missile self-destructs safely if control is lost. But given the secrecy and experimental nature of this missile, it is unclear how robust these safety systems are. Analysts have pointed out that the missile poses greater risk to Russia than to others if something goes wrong. Finally, maintenance and pre-launch checks. The interior engineering must allow servicing and maintenance. Given the heavy reactor module, shielding, warhead storage, the ground crew must be specially trained, and infrastructure must support radiation safety, reactor startup/shutdown procedures, cooling management, and transport of hazardous components. Observers identify the launch site has associated buildings likely for this purpose. In summary, the interior of the Burevestnik is a high-complexity, high-risk system. Nuclear reactor, propulsion, warhead, guidance, thermal management all packed into one missile. The sheer number of engineering challenges is enormous. On paper, this complex interior gives the missile huge promise: endurance, range, unpredictability, but in reality, it opens multiple failure points. Reactor meltdown risk, guidance failure, maintenance cost, radiation leak, detectability due to exhaust or radiation signature. Analysts argue that after more than a dozen tests, at least 13 since 2016, only 2 are believed partial successes. The interior is the heart of the system and arguably the weakest link. Moving on, let's examine performance. Russia claims the Burevestnik has unlimited range, can evade missile defenses, fly low, change course, and thereby bypass strategic deterrents. Some data suggests a claimed flight distance of 14,000 km in a 15-hour flight, 21 October 2025, though this claim is contested by experts. The missile's ability to fly at low altitude gives it a theoretical advantage over traditional ICBMs, which follow high arc trajectories and are easier to detect early. The nuclear propulsion means fuel range is not the limiting factor. Reactor heat provides extended endurance and therefore loiterability. Indeed, the term loiter implies the missile could circle for hours or days before striking, selecting unexpected paths and attacking from unexpected angles. Another performance feature is that with a nuclear reactor, it can maintain higher power levels, potentially enabling higher sustained speed or altitude variation for evasive actions. That in turn could allow it to avoid interception by defenses optimized for predictable ballistic trajectories. However, performance also entails major caveats. Experts argue that the missile is subsonic because it is a cruise missile, and flying long distances at low altitude exposes it to detection by radar, infrared, satellite, and air defense systems. When a missile flies low for many hours, its signature accumulates risk. One article states the missile will be as vulnerable as any cruise missile. Further, the nuclear reactor and exhaust plume may leave a radioactive trail or detectable signature, undermining stealth. The cost and complexity of maintenance, launch readiness, and reliability are significant. Indeed, some sources outright call the system more a political signaling tool than a viable operational weapon. In short, performance in theory is revolutionary unlimited range, unpredictable approach nuclear propulsion, but performance in practice is unproven, complex, and risky. The gap between claims and reality appears wide. Next up, safety features, or in this case, the worrying absence thereof. Given the interior design with a nuclear reactor, one would expect robust safety protocols. Reactor containment, emergency shutdown, radiation shielding, missile self-destruct systems fail, safe warhead mechanisms, safe transport and storage, leak detection, and environmental monitoring. But public information suggests many of these features are not transparently implemented, or at least, their reliability is uncertain. Experts voice concern that the missile may pose a greater hazard to Russia during testing or accidents than to its adversaries. For example, a 2019 accident reportedly linked to this missile project killed 5 Russian scientists when a test engine exploded, releasing radiation. Analysts claim that the missile's nuclear propulsion essentially makes it a dirty bomb. If used with a conventional warhead, because the reactor exhaust may spread radiation along the flight path. Other safety problems. Since the design requires very tight tolerances on reactor operation and missile guidance, failure to maintain the system could lead to unintended behavior crash, loss of control, dual risk of nuclear meltdown, or unintended detonation of the warhead. The radiation signature may make the missile easier to detect, but also endangers ground, crew, population in launch area, or unintended target zones. The logistical infrastructure required transport of nuclear modules, waste handling, maintenance creates huge safety burdens. U.S. officials have said the missile concept is nothing more than a flying Chernobyl because of its potential for radiological disaster. To summarize, safety features appear weaker than the promise. The concept of a nuclear-powered cruise missile demands extremely high safety standards, but public evidence suggests the missile is experimental, failure-prone, and inherently risky. The chance of a catastrophic accident is arguably higher than the chance of a flawless mission. Let's talk about unique selling points. What Russia is touting, and what this weapon allegedly brings. 1. Unlimited range. By using a nuclear reactor, the missile is not constrained by conventional fuel tanks. Russia claims theoretically unlimited range. That means it could strike from any direction, loiter near target areas, and bypass defensive geometry. 2. Unpredictable trajectory and low-altitude flight. As a cruise missile capable of low-altitude, terrain-hugging flight, the missile could appear from unexpected directions, forcing air defenses to search broad sectors rather than simple ballistic arcs. 3. Penetration of missile defense. Traditional missile defenses are centered around ballistic ICBMs, large radars detecting high-altitude trajectories. This weapon tries to evade those by different flight profile, long endurance, and abundant maneuver. 4. Strategic deterrence or shock effect. Even if the missile is not yet proven operational, the announcement alone serves as a strategic signal. Russia is pursuing next-generation weapons. The US and NATO have referred to the weapon as a major flash-to-the-world capability. 5. Loiter capability. The missile can hover or circle near target zones, wait for command or opportunity, then strike with little warning. The loiter capability is unique among strategic missiles. However, each USB comes with caveats. Unlimited range assumes reliable reactor and propulsion. Low-altitude maneuver increases vulnerability. Missile defense penetration claims are unproven. Strategic deterrence might rely on fear rather than function. Loitering creates risk of detection or unintended behavior, and cost and safety burden are enormous. Now, the price or cost aspect, though this is highly opaque. Because this missile is still under development, the exact unit cost is not publicly confirmed, but some facts give an indication of the expense and hidden costs. The infrastructure alone, launch pads, warhead storage, reactor modules is extensive. Satellite imagery shows dedicated launch pads at a facility north of Moscow, requiring huge investment. One article described the missile as a uniquely stupid weapon system because of its cost, risk, and low yield compared to other strategic systems. Although we cannot state a precise price in dollars, we can reliably say, developing a nuclear-powered cruise missile requires reactor research, shielding, propulsion engineering, new logistics, new safety protocols, testing, infrastructure construction, warhead integration, maintenance, and specialized transport. This likely puts unit cost, not just per missile but per launch facility, into the billions of dollars. When weighed against more mature ICBMs, the cost-benefit seems suspect. The price, therefore, is not just purchase cost but systemic investment and potential cost of failure: accidents, radiation leaks, failed tests. In the case of failure, the cost of cleanup, reputational damage, environmental harm, and de facto unusable system may outweigh the